what I mean by if A equal to B. So I'm going to substitute instead of BA. So basically, if I use the sign A plus B from the identity previously, which is sine A cosine B plus cosine A sine B. But if B and A is the same, that means this B will change into A. So I have sine A cosine A plus cosine A sine A. So these are the terms the same. That's why and because A and B is the same in here, A plus A is 2, so that's why sine 2A is this. So it's actually using the compound angle identity to work out the double angle identity. Now this is the sine 2A equal 2AB. We'll do the cosine as well, so we can use the same thing. I'm just going to use 2A straight away. So remember A plus B. Okay, I'm just going to write it. I don't want to use shortcuts now. Okay, so it's A plus B is the same as cosine A cosine B minus sine A sine B. Now we said A is equal to B, so that's 2A in here. This one it's cosine A minus sine A sine A. Okay, now that's cosine square A minus sine square A. So we know that's cosine square A plus sine square A is 1. So you can change the sine square into cosine by using the identity. 1 minus cosine square A. And that is given me, because that changed into plus, so that gives me 2 cosine square A minus 1. And that's the other identity. Alright, so those are the two identities that we're going to use today. Obviously, for the cosine 2A, I can, instead of changing the sine into cosine, I can change the cosine into sine. So I'll just write it in different. So I can rewrite this. And instead of this step here, changing the sine into cosine, I can change this cosine into sine, becomes 1 minus sine inverse A, and that's minus sine square A. Why did I say inverse? So that's minus, so become 1 minus 2 sine A. So that's the other way of cosine 2A. So cosine 2A has two identities. So cosine 2A either equal 2 cosine square A minus 1, or it's equal 1 minus 2 sine square A minus 1. Okay, so it's either way you can use it depending on the question. Okay, I'm going to start with a simple number question. Substituting, similar to the one that we did for the 10 in the previous example. Previous video. So for example, if I say find sine 2 theta if sine theta equal 1 over 3. So obviously you will have to use the sine 2 theta, the identity for the sine 2 theta. And the identity, sorry, I don't memorize them. 2 sine theta cosine theta. So 2 times 1/3 cosine theta. 2/3 cosine theta. Now The other piece of information in that question says theta is an acute angle. So theta is acute angle. Okay, so that means you will have to, because to find the cosine for that theta, knowing the sine is 1/3, you will have to use your Pythagoras. Otherwise, so remember trig ratio used for right angle triangles. So sine is opposite over hypotenuse. So the cosine using Pythagoras, and the cosine will give me, so it will be, if I use it in here, will be 9 minus 1. So square root of 8 is the cosine. Sorry, the other adjacent. So that means the cosine for theta is square root of 8 over 3. Now substituting back in here. Using your surds skills that you've learned them learned them during your complex number. So you can write the 8 as 4 times 2. Square 4 is a square number, so you take it out of the square, it becomes 2. So that's why your final answer here is 4 square root of 2 over 9, because 2 times 2. Okay, so yeah, that's your final answer. Okay, the next questions, obviously we'll have to do some proof, because that's the whole point of the trig identities, or the main points of trig identities. So let's say you want to prove this: cosine x plus sine x over plus, it's a long one, okay, so we've got this one here we'd like to prove. Obviously you will have to use one of the sides for sure. That the left hand side is way more complicated than the right hand side. This sec 2x means you will have to use the double angle identities somewhere in your answers, because you want to get 2x. At the moment we have only x. Now because we have two separate fractions in here, the common denominator between the two are just finding the common denominator, which is this one times that one, and that's and that helps me to rewrite everything as one fraction. So the common denominator is this. That means that times that. Then that one here, this times that. Okay, so I'm just combining the fractions into one. Now I'll start expanding, and then once after I expand, I'll start simplifying. So those two are the same, so that means the square, maybe. So I'm just gonna expand now. You can expand it the way that you want, but I'm just gonna use the square method to expand. So cosine square x plus 2 sine x cosine x plus sine square x. That's for this one here. Then I'll do the same here. Cosine square x minus 2 sine x cosine x plus sine square x, and then I'll expand the bottom one. That gives me, so the signs are the difference. That means there is no midterm in there, so that's why it's only cosine square x minus sine square x. Okay, now simplifying, the term will cancel out, and then I have 2 of each, so I'll end up with 2 cosine square x plus 2 sine square x. Now you will have to look back and you say, okay, which identities that I can use? Obviously, I know that the sine square plus cosine square is 1. So I can simplify the numerator by having 2 as a common factor and substituting instead of sine square, cosine square is 1. I'm just going to write it in here. Over. Now, cosine square minus sine square is, if you look back into the identities, if you have the identities with you, it's the same as cosine 2a. Okay, so cosine square x minus sine square x is the same as 2 cosine 2x. And this one is 1. So that's why you end up with 2 over 2, oops, cosine 2x. Now these two can simplify, so end up with 1 over cosine 2x. And obviously we know 1 over cosine is sec, so that's mean 1 over, sorry, that's cosine. That's why did I put the 2 in here, so that they don't simplify, because otherwise we won't get that. So that's how I've done something wrong. Okay, I'll just stop here. I'm just going to redo this one here. So cosine square x minus sine square x is the same as cosine 2x. So that's leave me with 2 over cosine 2x. Now cosine 1 over cosine is the 6, so that's y is the same as 2 sec 2x, which is proven. Okay, we'll do another example. Sine 3x equal 3 sine x minus 4 sine cube x. Okay, so now we will have to use the multiples of, first I have sine 3x on one side, I have sine x on the other side, so that means I'll have to use the compound angles to open it up, to convert from 3x to x. So the first thing, I'll convert this, I'll rewrite, so I'm going to use the left hand side. Start with the left hand side because that will open it up. The left hand side can be written as sine 2x plus x. Okay, because I want to get x only. That's why I'm trying to open it up. So then the sine 2x plus x is just applying the compound angle. Okay, now I still have 2x, so I will use the double angles now to open the 2x into x, because I only want x's in here. So the sine 2x is the same as 2 sine x cosine x. And the cosine x got nothing to do. I'm not going to change it. So that is this. Now the cosine 2x is the same as cosine square x minus sine square x. And then sine x in here. Now I'll start expanding. So that's the same as this. Now I'll start expanding, so I'll end up with 2 sine x cosine square x plus, expand this, you've got sine x cosine square x minus sine 3x. Okay, so you can see you've got the sine 3x. Now we've got everything in x. I don't have any cosine inverse here, so I'm going to change the cosine inverse into sine, because there is no cosine, so it's cosine square. I don't know why I keep saying inverse. The cosine square into sine, because the right hand side only has sine. So I'm going to use the other identity, which is 1 minus sine square. Now expand. Now collect the like terms. So you can see in here, I've got negative 2 sine to the power of 3, negative sine to the power of 3, and negative sine to the power of 3, and that gives me the negative 4 sine to the power of 3x. And looking at that, I've got 2 sine x plus sine x, and that gives me the 3 sine x, and that's the right hand side, so it's proven.